Charles' law. Charles's law. So again, we want to assume some sort of constant, right? And so let's come over here. So we must have some sort of constant condition. All right. Just sort of list that out. What we're always going to keep constant when we're referring to figure out these particular relationships is the number of particles. The number of particles. And that sort of makes sense if you keep the amount of substance that you're working with the same, then you can begin to isolate the different things, conditions, factors, variables that are having an effect, if they're having an effect whatsoever, right? So this right here is one, and we'll also, here in a second, we'll think about what the other condition has to be. You probably already figured it out, but let's sort of sketch this out. I always like sketching these things out, and I think it sort of helps with the learning if we can visualize it. So volume and temperature. So this is a situation where you can go back to elementary school and you can really use what they taught you. Oh, that looks like an upside down fish. I don't want that to look like an upside down fish. So that still looks like an upside down fish. I'm going to get it right. Ooh, that's more like what I was looking for. So let's think about this. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, that magic number 10. We don't need more, we don't need less. We could go with less, but 10 is a nice even number to work with. So this is a balloon. All right. There's a certain number of particles in there. It's fixed. So now let's think about this right here. We've got another balloon. Or actually, we're going to call this the same balloon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So let's look at the two. Let's look at the two conditions. Again, we know that this is going to be what we will sort of label our initial state. And then again, this is our changed state. So there's some volume here, and then there's some volume here. Obviously, there's an increase in volume here, right? And then here we have less volume. So let's go back to what you learned in elementary school. There's a lot from elementary school if you think about it. Most of what we know, most of what we kind of need to know, we learn the basics in elementary school. The rest of it is just learning fancy vocabulary as we get older. But the fundamentals, we pretty much get that early on. For this right here, the air that is outside of the balloon here and the air that is outside the balloon here is a certain amount of atmospheres, right? It's a certain amount of pressure. So the atmosphere in the room, remember, and we know that we can measure that in ATM, it's constant. Now remember, we've defined constant as that lowercase k, right? That's our constant. All right. So if we think about it, then the pressure is also constant. All right. So we don't have to grab the balloon and pull it out for those molecules to move outward. The only thing that we've done is change the temperature. And in elementary school, they do this thing where they take balloons and you blow some air into it, and then you'll leave one sitting out, and you call that your normal condition, right? Your what you're going to compare to, right? And then you'll put one like in the freezer, right? And then you'll put one near somewhere where it's heated up, right? So let's think about this. If you put it in the freezer, you decrease the temperature. You remember from elementary school that the balloon shrunk. It took up less space, which means a decrease in volume. there's still the same amount of particles. So let's assume that those particles don't escape. The air is still in there, right? Those particles are still in there. Now, eventually, over time, because of the substance, yes, those molecules will diffuse out through the membrane of that. But in the short time, those particles do not. In a very short period of time, those particles are trapped within that membrane, the balloon. Okay. Now, conversely, you know that when the temperature was increased, if you heat those particles up, that the balloon expands, right? If it warms up. So this goes back to the whole concept of the kinetic theory of matter. As energy is put into a system, as matter is heated up, it tends to move with greater molecular motion, and that greater molecular motion is going to cause those things to move outward, right? They will exert greater force upon each other. I'm not saying that the atmosphere has changed. I'm saying that the energy that the particles are getting from the surrounding atmosphere is causing the particles inside the balloon to change their condition. All right, but the pressure outside is still the same. You know, you haven't suddenly put it in a barometric chamber where you change the pressure and you're pushing down on it or decreasing how much you're pushing down on it. So if we look at this, we now have something that we can look at mathematically, right? All right, so we've got volume and temperature, right? We got volume and temperature, and so if you increase the temperature, we can see that you increase the volume. If you decrease the temperature, you can see you decrease the volume. That looks like something like that. All right. And volume, again, we're going to be measuring in liters. And temperature, we're going to measure it in something called a Kelvin, and that is a capital K, which is why we tend to write this with a lowercase k so we do not confuse it with the Kelvin. Now, there's another video that I have where I'll more in-depth explain the concept of the Kelvin. So I'm not going to do that here. We're just going to use that value, right? And so there'll be a, I'll link to that eventually here on this video for you, or in the description below. So let's think about this for a second. We've got temperature and we've got volume, right? So the volume was directly proportional to that change in temperature. So remember, this is our dependent variable, this is our response. That volume, it responded according to the change in that temperature. All as a result of some constant that was being met, right? In this case, we know it has to do with the pressure, the atmospheric pressure. So that also means that volume would be equal to the temperature, and these are capital V, a capital V and a capital T, times the constant, right? Which means that the constant here is equal to volume divided by temperature. So now, let's take what we've already discussed before. Let's go back to what your math teachers have taught you. What that means is we have an initial state where volume over temperature is what is occurring based on our constant. And then we have our change state where the exact same has to be true because, again, we're not changing the pressure. Our initial state is the first state. Our change state is our secondary state. And so you can see that we have another situation here where if we keep if the particles are stayed the same, and that's basically going to be true for all of these things, when we change the number of particles, that gets into another law. We'll talk about that later. Particles are the same, atmospheric pressure is the same. The only thing that is influencing back and forth is basically that change in temperature, which is affecting how much volume the gas is taking up. So we have a condition here where the initial state, we can set it equal to the final state. And this right here, this is Charles' law. Charles's law. Okay, this is Charles's law. All right, pretty simple, pretty straightforward. Again, once you have this, the math is going to be just plug and chug math. So let's look at an example. Again, I'm just making this up. I just put together some numbers real quick and did that. So we've got we've got a condition, and of course this isn't to scale. This is not to scale. All right. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll just use the number 10 again, so nothing changes. So we've got an initial condition where we are at our temperature equals 0 degrees Celsius. Okay, you got a temp probe, got your thermometer, and I know we talked about Kelvin up there. We're going to get to that in a second. But your thermometer, your temp probe that you're using, would always be measured in Celsius, right? And then you've got a certain volume here. Now remember, this is our initial condition, so we're just going to assign that a 1. So this is our initial condition. All right, initial state, same thing, right? And we've got a volume of, let's just say, 2,000 liters. Again, this is not to scale, not even remotely to scale. So now we're going to, let's just think about this. We're going to go from 0 degrees Celsius to 100 degrees Celsius. I know that is drastic, but I'm just trying to highlight this using using some numbers that are familiar. And again, let's see, I think I said that was 0 degrees Celsius. All right. Let me try this again. 0 degrees Celsius. All right. So we know from up here that if the temperature were to increase, that volume is going to increase. So we're going to want to draw something that sort of models that. We're going to want to draw something where it's taking up more space. And I'm being drastic with the amount of space it's taking up. But 2, 3, 4, 5, 6, 7, 8, 9, 10. Those particles, try to spread them out as evenly as possible. I know I didn't, but on a quiz or a test, we would make sure that we try to spread them out as evenly as possible. Now, at any given time, they're not going to necessarily be evenly dispersed, but for the most part, the sum of all of them are evenly dispersed, right? Because they're just moving back and forth. Eventually, it's going to reach what we call a state of equilibrium. Again, those are other videos. So we've got a volume here. And the question is what's that volume? All right. So we've got V1 over T1 equals V2 over T2. We're solving for V2, so we do some pretty basic math here, just like your math teachers taught you. We want to isolate V2, so we're going to multiply this side by the second temperature, so we're going to multiply this side by the second temperature. So we would get V2 equals V1 T2 over T1. That's the new form of our equation to solve for this condition. All right? When a condition is like this is what we solve for. So now there's one more thing we have to remember is that we're looking at Kelvin. All right? And the Kelvin scale, again, without getting into the details, but it has everything to do with taking into account absolute zero. And so, again, there's more detail in another video that I have for you, but it was theorized mathematically, and we've gotten close to this, that the relationship between volume and temperature, that with a gas, that you could get as close to a volume of 0 at absolute 0, which theoretically was defined as Kelvin 273.15. So what we have to do is whenever you have a temperature, you have to essentially add 273.15. So we're always going to add 273.15 to account for our Kelvin. Okay, to account for our Kelvin scale. All right. So V2 equals, all right, V2 equals, so that means, so volume 1 was 2,000 liters, 2,000 liters, right? Temperature T2 is 100, well 100 plus the 273.15, so that would be 373.15, and then we just put K, okay? And you don't use a degree symbol with Kelvin, all right? You do not use a degree symbol with Kelvin. And then T1 was 0. Well, 0 plus 273.15 is 273.15 K. All right? Units cross out, it's about those units. It's always about the units. All right, so V2 equals, let's see what we got here. So we've got 373.15 times 2,000 divided by 273.15, we get 273.199. There's several other numbers. You don't need them. And then, of course, the only unit left is liters, which is good. We're solving for volume. So let's evaluate this down to something that kind of makes sense. I mean, significant digits. Here's, this gets a little tricky. So we started off with 2,000. That's the way that's written without a decimal. It looks like 4, right? So we can think of that as 2,000 point at a minimum. So that'd be 4, or 2,000.0. We notice 273.15 is 5 significant digits. We have an answer here that's in the thousands, and so to account for even that's a minimum of 4 significant digits. So we realize that probably when we're doing this, and when we get answers like this, 5 at a minimum is going to be what we're going to want for significant digits, right? 5, because that would put us, in this case, 1 place past a decimal. So again, significant digits are all about knowing how many you're starting and working with, looking at measured values, but then also take into account what makes sense, what is practical for the condition that we're working with. So for training purposes, we can go with 5 significant digits, which would be 1, 2, 3, 4, 5, and so 2,733.2 liters. All right, and of course 0.199. That's pretty close to 0.2. So if you have 19.9 cents, I mean, you might as well have 20 cents, right? So this kind of makes sense. Now let's evaluate this and make sure the numbers should make sense. That we saw here that there was an increase in temperature. It was quite a lot of temperature, right? So does it make sense that the volume would increase? And according to what we looked at up here, and what we remember from elementary school, yeah, that makes sense. That makes sense that if you decrease the temperature, you decrease the volume, and vice versa. Well, right here, we see the exact same thing happening. So we know that our relationship, we know that accounting for our constant here, that we've got a proportional relationship, and then evaluating this for our constant, getting this form of the equation for the first condition and setting it equal to the condition of the new state of those gases makes sense, because we get a larger value than what we started with. We have a greater volume in our calculation than what we started with initially in our given data. So this makes sense. All right, so that's Charles' law in a nutshell. A common error I see with this is people just forget to convert to Kelvin, and then they wonder why their numbers are off. And so you can see, since you're multiplying a value by X amount plus 273, and you're dividing, in this case, by X amount plus 273, if you don't account for that, you get a serious disparity in your numbers. And so if your numbers are wrong, when your calculations are wrong, that should be probably the first thing you think about is, wait a minute, did I account for the Kelvin scale? Did I convert my units from Celsius to Kelvin? And I know a lot of people are also, you tend to get in the habit in math class or when you're in a rush. And I do the same thing myself sometimes, but although I broke myself with a habit, I had to. People tend to do a lot of math, and what they don't do is they include that unit with the number. Never write a number without a unit, ever. Almost basically 100% of the questions that any students will ask me where they're confused, and it all boils down to they write these numbers into the equation and just want to plug a unit in at the end. And I know the reason for that is because you tend to be in a lot of math classes where it's just about getting the right answer. So you just plug numbers in, and then you go, oh, what am I solving for? I'm solving for this, and you just add that unit. And that's all well and good under very informal conditions. But when you have to rely on evaluating your answer with something like this, you need to make sure that you're including the unit with your number. All right. Hope that helps, and keep watching the videos in this series. There's lots of videos for gases. Gas laws are pretty. They're pretty neat. There's some really fun lab stuff we can do with this. So study, and I'll see you for another video soon.